So last time we left off with these four common summation formulas. This one right here, hopefully you see, is kind of a no-brainer. Anytime you have a constant and you're adding up a bunch of the same constant over and over and over again, it's just multiplication. Multiplication is repeated addition, so that's where that one comes from. This one you guys developed on your own, sort of. That one's going to be used a lot, so you need to have that one memorized. You're going to use it, you're actually going to probably memorize it just through repetition. So that one shouldn't be too big a deal, you should know it automatically. This one you're probably going to also memorize through repetition as well, but you're not going to use it as extensively as this one here. So do try to memorize that one. This one you might not memorize through repetition, but you do need to know it because it does pop up, like on a test or something like that. It could be there. So all four of these you do need to know, but they go kind of in order of how you're going to see the frequency at which you'll see them. All right, example problem. We have to evaluate the sum from I equals 1 to n of this expression right here, I plus 1 over n squared, for n equals those things. So we'll worry about n equals 10, 100, 1,000, and 10,000 once we get done evaluating, basically converting from this format to the algebraic format. So the first thing we want to do is recognition of constants. Do we have any constants in this that can be pulled out? Because if you remember those rules for summations, if we have a constant, we can pull it out. Is there one here? Yes, there is. The rules for summations say that this number right here has to be a constant. The I equals 1, the lower bound, can't change. As we start doing our iteration, then that number does change, but the lower bound does not change, and neither does the upper bound. That's a constant also, okay? So n is a constant, which means that this n squared in the denominator is also a constant. So it can be pulled out, okay? When I pull that out, though, it's not going to be n squared. What is it going to be? 1 over n squared. So I'm going to rewrite this as the sum from I equals 1 to n. I pulled the 1 over n squared out, and I'm left with I plus 1. Okay? Now we have this other property that says if I'm adding two things together in a summation, or subtracting them, but in this case I'm adding them, then I can split that into two separate summations. Okay? So I'm going to do that. I have the 1 over n squared sitting out front, and I've split this summation now into I plus 1. Once you're to this point, you've turned your summations into things that we can convert into the algebraic version. We have the sum from I equals 1 to n of I, which is this guy right here. We have the sum from I equals 1 to n of 1, a constant, which is this guy right here. So now we can convert the summations into algebra. And then from there, we'll be able to evaluate down, okay? So I'm going to do that here. I have the 1 over n squared still. And then inside, the sum from I equals 1 to n of I turns into n times n plus 1, all divided by 2. And then the sum of I equals 1 to n of 1 turns into n times 1, or just n. So I have plus n. Now we simplify. Yeah, so you could distribute, you could form common denominators and simplify. Okay, you have some options, but this does simplify. So I'm out of room, I'll go up here. We have two distributions that need to happen. Which one do you want to do first? The inside one? Okay. So we still have the 1 over n squared out front. And then inside we have n squared plus n over 2. And then still the plus n over here. Okay, you could go common denominator, or you could distribute the 1 over n squared in, right? You want to do a common denominator? No? Let's distribute the 1 over n squared in. We get n squared plus n over n squared times 2 plus n over n squared. Now do a common denominator? You really want that common denominator. What else could we do right now? Yeah, reduce. So we have an n, we have a factor of n in the numerator here that we distributed in. Where was it? Over here. We distributed that n in, and it turns out we didn't need to because that factor is going to divide out with another n in the denominator. So we have that n that's going to divide out here, which leaves me with the n plus 1 over 2n. And then this is going to reduce as well to 1 over n. Do we need to do a common denominator now? Should we do a common denominator now? Okay, fine. So, common denominator is going to be 2n. So if I put a 2 there, I'll make that a 2. And that gives me n plus 3 over 2n. Can I simplify down any farther than that? No. No, you don't want to. Otherwise, you'd be splitting it back up when you just went to all that effort to put it together. Okay. So here's our simplified answer right here. In other words, the sum from I equals 1 to n of this expression can be turned into this right here. So now it says evaluate for n equals 10, 100, 1,000, and 10,000. So let's do that. I'm going to try to squeeze in a little table here. Go 10, 100, 1,000, and 10,000. I did. Okay, so usually a calculator is going to be your best bet here. If I take 10 plus 3 is 13 divided by 20. What's 13 divided by 20? On your calculator. It's probably not 9/8. Okay, 0.65. Now 100. The nice thing about using the calculator is you can just go back up and change the 0 to, or change the 10 to, yeah. No, you can't just move the decimal over. That doesn't work. Yeah. What'd you get? 0.515, okay. And then for 1,000? $5015, okay. And then for 10,000? 50015. Okay, so the question at the bottom, look at the results. What do the answers appear to be doing? Okay, I don't want the pattern. I want, like, in terms of calculus, what are the answers doing? Getting closer to 0.5. So what could you say in terms of calculus, and if there was an asymptote, if you're looking at the graph, that asymptote would be at 1/2. So therefore, as n gets, finish my sentence, as n gets closer to infinity, the sum approaches 1/2. Okay? So quickly we get back into sort of the language of calculus. Even though we're basically just doing algebra here, there was no calculus involved. We can see that we could start applying some calculus and take the limit as n goes to infinity. And if we did that, then we'd be able to determine what the actual sum is. Okay? Even though we're adding up forever, we get a sum that approaches 1/2. Okay? It's kind of interesting, I think. we've been working towards this for the entire section. Starting off with looking at area and trying to geometrically figure out what the area is going to be, and then switching over to summations so that you remembered and learn how to work with summations a little bit. Now we're going to put the two together and try to figure out the area underneath a curve using summations. Okay? So how to find the upper and lower sums for a region. So think back to the beginning of the section when we were looking at area. Okay? First thing you want to do is determine the width n rectangle, the width of n rectangles over the interval. So each rectangle is going to have the same width, and you're going to be given some sort of interval from 0 to 2 or from 1 to 5 or something like that. Okay? So my example is f of x equals x squared. So we're going to find the area underneath f of x equals x squared from 0 to 2. Okay? So if I were to draw a little sketch of that real quick, it would be a parabola, of course, but I'm only going from 0 to 2, so I'll just show this. Here's 0, here's 2. Okay? I'm trying to find this area here. I'm going to do that by basically drawing a bunch of rectangles. Okay? All right, so how do we determine the width of each rectangle if I want n rectangles? We talked about this already. You take the far end point of the interval minus the near end point of the interval to get this total distance right here. And if I say I want 4 rectangles, then you would divide that by 4, right? If I want 8 rectangles, then I'd divide it by 8. If I want n rectangles, then I'm going to divide it by n. So if I call this A and this B, then to calculate the number of or the width of each rectangle, I need to do B minus A over n. Okay? Now I'm going to call that width delta x. The change in x is the width for each rectangle. So if I have an x value of 0 and my width is 0.5, then the change in x from one rectangle to the next would be 0.5. And then from one rectangle to the next would be another 0.5. One rectangle to the next would be another 0.5. Okay? So that's why I'm calling it delta x equals b minus a over n. So in my example, delta x equals 2 minus 0. 2 minus 0. This would be a, this would be b, just like I have over here, divided by n. I don't know how many rectangles I want, so I'm leaving it as n. If I knew I wanted 8, then I'd put 8 right there, but I don't. I just have n. So you reduce that and you get 2 over n for delta x. Okay? All right. You're just nodding your heads because you don't know what else to do? Okay. Then, once you've determined the width of each rectangle, remember, this is the width of each rectangle right here. Determine the x-coordinate, and the x-coordinate is called c sub I. Determine the x-coordinate of each rectangle over the interval. So now I have all these rectangles here. All of them have this width to them. I don't know how many I have, but I know that they have this width, and I know that I have some number of rectangles. Each left endpoint, I'm going to call c sub I. The reason I'm calling it c sub I is because I'm going to set up a summation where I equals 1, meaning rectangle 1, and then I will count rectangle 2, rectangle 3. So c sub 1, c sub 2, c sub 3. Okay? So I have to use this general notation in order to let me do that. So, determine the x-coordinate c sub I over each rectangle over the interval. I have left endpoints and I have right endpoints. So these are your c sub I equations for left endpoints and right endpoints. Why are these equations there? Why are they that? Why aren't they something else? Is the question. To show you that, I need to draw a little sketch. And I'm just going to draw a general curve. I don't know. It's not necessarily x squared. It's not necessarily a parabola. It's just a general curve. Okay? I'm going from A to B. Somewhere over this interval, underneath this curve, is a rectangle. And I'll just set it up so that it's left endpoints. There's a rectangle under this curve. Okay? It's one rectangle. There's like many rectangles under here. I'm just showing one. Okay? Which rectangle am I at? Yes, you do. It's not C sub I. Does that look like the first rectangle?
No, I don't know. I'm just guessing.
What was that? The ith rectangle. That's right. Okay? I don't know what rectangle it is. You were just guessing. When you don't know something, it's a variable. The only variable we have here is I. Ith rectangle. This would be the first rectangle all the way over here, but I don't know how wide they are, right? I'm just representing a rectangle here. It could be that wide, but it could be incredibly skinny to the point where I could never draw it. Okay? This is the ith rectangle. We have passed how many rectangles before this one? No. I minus 1. If this is the 10th rectangle, then how many rectangles have we passed? 9. So if this is the ith rectangle, then we've passed I minus 1 rectangles. Okay? All right. The x-coordinate of this, because of the fact that I'm using my left endpoints here, I need this x-coordinate right here. Okay? So that when I plug in that x-coordinate, I get the height of the function. So I need to know this distance right here, all the way back to the origin, including that distance right there, all the way over to this rectangle. What is that distance? No. The width of the rectangle is delta x. But how do I get there? Tell you what, let me change my sketch a little bit. Maybe this will help. I'm going to move A over. Here's A. I need to know this x-coordinate right here. Close. A, for sure. This distance right here is A, right? So that gets me to here. If I add all the rectangles together to get me to this rectangle, so if I add a delta x to it, right? Or if I add an I to it, that's what I should say. If I add I to it, because that tells me how many, that I've gone one more rectangle from A, right? So A plus I gets me one rectangle farther. A plus 2I gets me 2 rectangles farther, and so on, okay? But each time I do that, I'm using which side of a rectangle? The right side or the left side? I'm using the right side. So if I add A plus I times delta x, the width of the rectangle each time, times the number of rectangles that I've used, that gets me to here. So I have to go I minus 1 to get me back to here. So technically I'm going back one rectangle, but because this rectangle shares the same side as this rectangle, I get the x-coordinate that I'm looking for. Okay? So that's where the A plus I minus 1 times delta x comes from. Because I need to go back so that I'm now on the left side of the rectangle that I'm looking at. So it's incredibly important that you understand that concept. This is the correct formula that you're going to use all the time. But you need to understand why it is what it is. Okay? It comes from this sketch right here. Now for right endpoints, C sub I this time is going to be this distance A, and then I'm going to take I times delta x to get me to that distance that I've gone, but this time I'm using right endpoints. Because I'm going I times delta x, that's the right endpoint every time anyway, so that's why it's just A plus I times delta x for right endpoints. So now that I've explained that, let's go over to the example again. We're back to x squared between 0 and 2. We've calculated delta x, 2 minus 0 divided by n, so it becomes 2 over n. Using left endpoints, so I'm using C sub I. I have to calculate C sub I. What is C sub I? The x-coordinate of where we're at. Okay? So, C sub I using left endpoints, because of the fact that A is 0 here, we get a 0 there, plus I minus 1, it's always going to be I minus 1, times delta x, which we calculated was 2 over n, and then we simplify that down. So we get 2 times I minus 1 over n. That's my c sub I, the x-coordinate of where we're at. Okay? Using right endpoints instead, we use this equation. A is still 0, so we plug 0 in there, and then it's just plus I times delta x. So that's plus I times the 2 over n, which simplifies down to 2I over n. That's the x-coordinate of where we're at for right endpoints. Here's where it gets a little tricky. So step 3. Remember that the area of a rectangle is what? Base times height. So the base of the rectangle is delta x. Let me put a little sketch back on here. Here's my thing. I got this rectangle sitting here. The base is delta x, the width of the rectangle. Okay? What's the height? It's not c sub I. It's f at c sub I. So you have to substitute c sub I into the function to get the y coordinate. Okay? But then once you have the y coordinate, you have the height of the rectangle. And once you have the height of the rectangle, you can multiply those two together to get the area of that one particular rectangle, your ith rectangle. It's not brutal. Well, it seems brutal, but it's not. Actually, I think it's a kind of elegant thing to do. Okay? It's almost like prom. Okay, so remember that the area of each rectangle is base times height. The base is delta x. The height is the function evaluated at each c sub I. So what you need to do is take your c sub I, whatever it is, and plug it into the function. That's this right here. That's your height. This, delta x, is your what? The base, or the width. Yep. And I'm multiplying those two together. So I'm getting height times width, which means that for each individual rectangle that I create, each rectangle, the ith rectangle, I just calculated the area for it. So now I'm adding up all of those areas by using a summation. And because I'm adding up all the areas, overall, I will wind up with the total area underneath this curve. If I let n get smaller and smaller and smaller, then I wind up with an infinitely large number of rectangles, each of infinitely tiny width, which means I've reduced the amount of error to 0, and I wind up with the exact amount of area underneath the curve. Okay? So that's where this is heading. So back to our problem, using left endpoints, we're going to call it now a function S of n. So you can think of that as like the sum of n rectangles or something like that if you wanted to, equals the sum from I equals 1 to n of my function evaluated at c sub I. If I was using left endpoints, then I had that 2 times I minus 1 over n that I just plugged in to my function, which was x squared. Okay, so we'll get there. Times delta x, which is 2 over n. So then I evaluate the 2 times I minus 1 over n, plug it into my function, which was x squared. That's x squared right there. Plugged it in, so I wind up with 2 times I minus 1 over n squared times the delta x still, 2 over n. If I was using my right endpoints, it's the same setup. I don't know why that's capital and that's small. They should be the same. So one or the other, doesn't matter to me. Equals the sum from I equals 1 to n of the function evaluated at my c sub I this time is 2I over n times the delta x, 2 over n. Substitute it into my function. Again, that's x squared right there. So it becomes 2I over n squared times 2 over n, my delta x. And then I simplify. So on this guy, my left sum, which is here, I'd probably distribute and then send that square in. It's going to involve some foiling. I have a delta x that I'd also distribute in. And once I'm done with all that math, I wind up simplified down to this right here. For the right sum, same idea. Distribute. This is actually distributing the exponent in. 4I squared over n squared times 2 over n, which gives me 8I to the third over n to the third. Okay? This one right here, if I distribute that in 2I minus 2 over n, but I have to square that, so I wind up with 4I squared minus 4I plus 4. Is that right? Nobody knows? I don't think it's 4. I think it's 8 minus 8I. You guys are just trusting me at this point? Is that because you're lost? Oh, okay. So I distributed that in, and then I'm foiling the top. Okay? Divided by n still. Squared, thank you, times the 2 over n. That's still outside. So I distribute that in, and now I have 8I squared minus 16I plus 8 over n to the third. This is still a summation at this point. Okay, I don't know, I didn't include it there, but I should have. So, and the same thing is probably true here. That should be there. So we're still summing here, and we're still summing here. Now we do what we did in those previous two problems, or that previous problem where we simplified down, convert it to algebra instead of a summation. So this is where some seriously heavy lifting comes in. I'll take care of this one here first, okay? One over n to the third. Sum I equals 1 to n, 8I squared minus 16I plus 8. We can also factor the 8 out, that's right. So it's not just the n to the third, it's actually 8 over n to the third that we're going to factor out of here, which gives me 1I squared minus 2I plus 1. Now we split it all up, so we have the 8 over n to the third times sum from I equals 1 to n of I squared. We know that one. Minus, we have sum 2I. I'm going to pull that 2 out as well. 2 sum I equals 1 to n of just I. We know that one. And then we have the plus sum I equals 1 to n of 1. Okay, so now we have 8 over n to the third times I squared is okay, so that takes care of that one. Then minus 2 times over 2, okay? And then plus n. 1 times n is n. Okay, so now the sums are gone. Let me do us all a favor and put this up here because that's what we're feeling right now, but we have to continue. Okay. So, simplify. I see a couple things that can happen right away. Not crying. There is going to be an n that goes away. So let me change colors. Do you see it? We have divided by n to the third here, and there's a factor of n in this one, there's a factor of n in this one, and there's a factor of n in this one. So I can make that a 2 and get rid of each of those n's, turn this one into a 1. That saves me a little bit of effort at least. Anything else that can immediately disappear? I heard it somewhere, the 2's. There's a 2 here and a 2 here that are gone. The n changed to a 1 because I sent an n in out of this n to the third. There's an n here, they're gone. There's an n here, they're gone. There's an n divided by n here, so it turned to 1. Okay. I'm just trying to make it so that I don't have to write so many steps down. Okay. Anything else? Or maybe we're to a point where we're not sure, so we should continue. Okay, so let's continue. I still have the 8 over n squared out front. And now inside, what should I do? Distribute for fun? Okay.
Hold off on that.
Well, couldn't you? Well, I don't know.
Tell you what, let me write this down. Let me write it down as we have it, because I think all the little stuff is confusing everybody. So we have the n plus 1 times 2n plus 1 divided by 6. And then this has turned into minus, in parentheses still, n plus 1,
Can we?
and then plus 1. This becomes minus n minus 1 plus 1. So those 1's disappear, which is nice. So let me rewrite this now. 8 over n squared times the n plus 1 times 2n plus 1 over 6 minus n. Now what? Distribute what? So you want to FOIL? We should FOIL. 8 over n squared times, FOIL this. Plus 3n plus 1 over 6 minus n. Distribute the other thing. What's the other thing? Okay, so you want to distribute that all in? Okay. All the way completely? All right. So what do I get? So 24 and you did simplify it there, and you could have done that, but I wanted to write it all down. So, okay, here's where we're at. Everything, all the parentheses are now gone. Now what?
Well, we can factor out
2.
So I can reduce.
Yeah.
This becomes 8. I'm going to give you some advice right here.
Pull out the end.
Because of this 8n over n, which we know is going to turn into
Split all the other stuff up too.
minus 8 over n, split everything up, and then you're going to have another like term to combine. So split everything up now and reduce as you go. So 16n squared divided by 6n squared becomes 8 over 3.
Okay.
Plus
The n's are gone.
Yeah.
Okay, plus 4
4 over
over n plus 4 over 3n squared. And then this one is minus 8 over n.
Now we can combine those.
Like terms, so we have 8 thirds plus, no, come on, minus 4 over n, look at that, plus, okay, that seems to be as far as we can go. If I go back up here, there it is. So all that work, wasn't it much better when I just had it sitting right there as the answer? Yeah, but that's all the work that has to go into getting here with left endpoints. But it says simplify, we did that, and take the limit as n goes to infinity. This is the easy part. Here I am all the way down here. If I now take the limit as n goes to infinity, I plug infinity in for n, and what happens here? What happens here? So what do I get as an answer? 8/3. So the area under the curve for x squared from 0 to 2 is 8/3. Okay? It is 8/3. There's no error in that at all. Because we let the number of rectangles go to infinity, which means that they had an infinitely small width. There you go. All right, we're going to do the same thing with right endpoints now. So we have, for right endpoints, we have this guy sitting here. No. Do not do that. So we have, let me just rewrite it here. I equals 1 to n of 8i to the third over n to the third. What can I do? Pull out the constants. What are my constants? So 8 over n to the third. 8 over n to the third, sum I equals 1 to n of I to the third. Yeah, that's one of our special ones. So we can convert right now. We have 8 over n to the third times let's reduce. Hold on. We have an 8 divided by 4 here. Notice that these are all being multiplied together. So there's a lot of reducing we can do here. 8 divided by 4, that becomes a 1, that becomes a 2. N squared here, n to the third here. The n squared here is gone completely, and the n to the third becomes n to the first. I have this n plus 1 squared here. I can't do anything with it. I've reduced this down as much as I can. So rewrite it. I'm left with 2 over n out front times n plus 1 squared. Now FOIL. 2 over n times n squared plus 2n plus 1. Now what? Send it in. So we get 2n squared over n plus 4n over n plus 2 over n. Now what? Reduce. This becomes 2n yeah, I think we did something wrong. 2 over n. Let me check it. Yeah, the mistake is right here. That's a 2, not a 2i. So this should just be squared. So let me back up. This is just I squared here. So let me erase that. Okay. So starting over, we have the 8 over n to the third still. Sum from I equals 1 to n of I squared. So we have 8 over n to the third times okay, still reducing. This n goes away, but this is now squared. That makes it better. As soon as I saw that n and that 2n in there, I knew something was wrong. So then we're going to reduce this with a factor of 2, so that's going to be a 4. We're going to FOIL that. So I have the 4 over n squared times over 3. Now I can send the 4 over n squared in. I have 8n squared over n squared. This is going to work out much better. Plus 12n over 3n squared. Over 3n squared, thank you. Plus 4 over 3n squared. Now reduce. This becomes 8/3 plus 4 over n plus 4 over 3n squared. Slightly different result, but it is what I have up here. Slightly different just in sign right here. Doesn't matter because when we take the limit, it's just going to disappear. So I take the limit as n goes to infinity, and these two guys disappear, and I'm left with 8/3. Doesn't matter which sum you use, you're going to wind up with the same answer in the end because the number of rectangles goes to infinity. they become infinitely small, okay? So which one looks better?
Right.
Right sums typically are what people prefer. So when you're doing this on the homework,
You don't have to do one.
unless it specifically says to use left sums, or it specifically says to use left sums and right sums,
Which it does at one point.
then you can use whichever one you want. For me, my money's on right sums. It's easier to work with, okay? There are times, though, when you're not going to take the limit as n goes to infinity. You might just let n be 4 and 8 and 10 and stuff like that, and then I could make you compare left sums and right sums by doing that to see what the differences are and things like that. So you do need to know both.